So I think I don't have to write a proof for that and also not for that. Another property of the type that we should note is that if such that pattern is minimal index. Minimal index, maybe we'll give it a name. L, maybe R of L. So it's R of L is the log to the basis Q of this minimal index. I'll tell you already now, I will prove it later on, but somehow I want to explain later on that this R of L is going to express for us, in some sense, the distance on the building between L0 and L, the equivalent class of L0 and L. We'll talk about that. So R of L, so I start with L, I multiply it by some power of pi, negative or positive power of pi, to make it to have a minimal index inside L0. That's the index must be a power of Q. That's always submodules of L are always of powers of Q. And that power of Q, it will be Q to the something, Q to the R. So I'll call it R of L now. And if you want, again, that's, if you want, tau of L, of equivalent classes of L, is really R of L mod D. Right? Because that's what we said before. Before we said that you can take any representative, you can multiply it by pi, by I power of pi, to put it inside L0. It doesn't matter what will you do. If you take the index, log of the index, mod L, this is the color. In particular, if you do it with the minimal one, it's okay. Okay. I want to say that vertices, two neighboring vertices and two neighboring vertices have different color. And this is basically clear. And because you see, if L1 is inside L2 and this is inside pi L2, and now I multiply everything by something to make it in, I can really replace them both by the same power somehow in order to make that it will be inside L0. I can always take representatives which are in L0, so I can assume that L2 is already here. So the index here and the index here are different than each other, modulo D, because this is of some index Q to the R, and this one is of index Q to the R plus D. Right? If I multiply by pi, I'm adding D to the exponent. The index here is Q to the R. The index from here to here is Q to the R plus D, because this is multiplication by pi from here. So L1 is strictly inside L2 and strictly contained pi L2. Then its index is Q to the something between R to R plus D. Neither R nor R plus D. So if I take it modulo D, it's different than R modulo D. So two neighboring lattices necessarily have different colors, okay? So in some sense, this is a coloring of the graph. It's a legitimate coloring of the graph. But in particular, a maximal cell which contains, right, a maximal cell which, as we remember, has dimension d minus 1 and n's contained d vertices, has all colors, each one exactly once. Yeah, if I take a d minus 1 cell, a d minus 1 cell has d points, all of them are connected to each other because this is a cell. By definition, you remember, in a simplicial complex, if we have a triangle, then it means that every two are connected. If we have a pyramid, every two are connected, right? Every subset is also. Yes. So they have different colors. Now, altogether, I have d different colors, right? Everything is in z mod dz. So I'm getting exactly, so this gives us kind of a beautiful coloring of the vertices of the building, so that all maximal cells are colored by all the d possible colors. Next, let's relate it now to the group structure, to the action of the group. The group GLDF acts on the lattices. Action of GLDF. The group GLDF acts on the lattices. Well, let's be careful. It does not okay, first of all, it acts on the lattices. Well, that's clear. We take a matrix, we take a lattice and multiply the lattice by a matrix, and we are getting another lattice, right? We take a basis, we multiply it by a matrix, we get another basis. In fact, it acts transitively. Transitively, namely, I can go from every lattice to another lattice by multiplication by an invertible matrix in GLD, because I can take every basis to every basis by invertible matrix. Okay. Now, the center of GLD, F, which is simply the invertible matrices, the scalar matrices, preserves equivalent classes, because what does it do? It just take you a lattice to multiply it by t, and therefore the quotient group PGL DF acts on the vertices, on the equivalent classes. I had to say, okay, maybe say, I can say it now, an easy claim, easy exercise, I'll just explain it. PGL DF preserves the combinatorial structure. Namely, it preserves the connection. It takes I cells to I cells. And this is pretty trivial. A quick way to say it is to use the, here it's maybe better to think as Uriah presented last time, that everything in the building really depends on the I skeleton. If you know the graph, the meaning of the exercise I gave you before, which is the connection between Uriah's definition and my definition, the meaning of that is that in a building, everything depends on the one skeleton. If you know the graph, you know everything. Because what are the I cells? The I cells are just those subsets of size I plus 1, which are cliques, which every two of them are connected by an edge. So if you know the edge, if you know the one skeleton, namely you know the graph structure, just vertices and edges, you know everything. So if I know that the graph is preserved, then everything is preserved. So what I have to prove here? I have to prove that if I take an invertible matrix and I multiply, and I have two lattices which are equivalent, which are neighbor of each other, and I multiply them by a matrix, then I have to prove that they are still neighbor of each other. But this is trivial. Because if L1 is contain L2 and this contains pi L1, and I multiply by G, then GL1 contains GL2, contains pi GL1, which is equal to G pi L1, because G is a linear map. This is completely trivial, that the group preserved the combinatorial structure. The important thing from our point of view is that the building is very symmetric in the sense that what you see in one vertex, what you see in a neighborhood of one vertex is what you see all the way in every other vertex. So we have a transitive action which preserves everything so that everything looks the same. Let's analyze this a little bit further by checking two things. First of all, I want to check what does the action do to the coloring. And here we have to be a bit careful. It's a little bit technical, but I want to do it because we will need it later at some later point. Let's see what happens. So warning. The action of PGL DF does not preserve the coloring, preserve tau. By the way, even without thinking, how do you know that it does not preserve the coloring? Right, it's transitive. It acts transitively on the vertices, so every vertex can move to every vertex, which means in particular vertices of different color can move to each other. So we know for sure that it does not preserve. But let's see how it acts. You can really understand how it acts because you see, let's look at an element G in GLDF. And let L be something like O alpha 1 plus O alpha D. One way, if you remember, one way which I told you, why don't we use this, even though we didn't solve it, I gave you this as an exercise, but it was not a difficult exercise. You remember I told you take M alpha 1 up to alpha D, the matrix. And the tau of L was really, we take the determinant of M and we take the valuation of this, mod D. Right? This was the coloring of L. Now let's see what would happen if we what would happen if we apply G on that L? What would happen to the coloring? So G of L will be O. I can take G is linear map, so multiplication by O can be taken outside. But this is O of G of alpha 1 plus O of G alpha D. Now, this is the matrix, I'll write it M of L, like associated with L. What happens, what is the matrix now which we associate with GL? We take the basis here, which is G alpha 1, G alpha 2, G alpha D, right? This is the matrix associated with the image of L. But this matrix is exactly like, think about multiplication of matrices. I multiply the first column by G, the second column by G, etc. So this is the same as G times M of L. You agree? If you multiply, G is a matrix itself, it's a D by D invertible matrix. I multiply by a matrix L. By a matrix M. This is not an invertible matrix necessarily. Or well, it is invertible in F, but not in O. Okay, so now I have to compute what is tau of GL. So I have to compute the valuation of the determinant of the matrix MGL. This is equal to the valuation of the determinant of G times ML. Well, everything is, after that we'll have to take it mod D. And this is equal to the valuation of the determinant of G times the determinant of ML. Right? Determinant is multiplicative. Valuation is additive. It takes multiplication to addition. Right? So this is the valuation of the determinant of G plus the valuation of the determinant of ML. Okay, and now I'll take on everything mod D. And all these equivalent, I really care about them. They are true without mod D, but I really care about everything mod D. So what does it mean? So what does it mean? So G preserves the colors, if and only if, you see, in order to preserve the color, what I mean that this valuation is zero, well, zero mod D. Because the way it pushes the coloring, it really pushes the coloring by adding valuation of the determinant of G to the original color. If and only if the valuation of the determinant of G is equal to 0 mod D. Okay. Fair enough. We have a criterion which are the matrices. So I can just denote G plus, say, I don't know if this is the standard. This is the standard operation.
G plus, G0.
It's G0.
Very
G plus is another maybe G0. Z0 will be all G such that G preserve colors, reserve star. So what do we know about? So first I claim the node then the claim is 1. First of all, this is a subgroup. Well, that's one to prove in several different ways, but for example, you can say that it contains, let's see, it contains, first of all, SLDF, all the matrices of determinant 1, of course, reserves the color, because for them the determinant is 1, the valuation is 1, is exactly 0.
What PSLD there?
I can talk about coloring even before. A coloring of a lattice is a coloring of its equivalent class. I can talk about either this or this, it doesn't matter, so it's really good. And also, now note that, let's see about the quotient, GLDF over GL over SLD is isomorphic to F star. But we know that F star is isomorphic to pi to the z. It's kind of it's a cross O star. We basically saw that when we talk about the fields, that every element, every invertible element in the field can be written uniquely as pi to the integer times an invertible element of O star. So I can really write it as a direct product. And if I get a matrix here, and the isomorphism is really via the determinant, right? We have a determinant map from here to this group, and the kernel is SLD. Okay. Now, what happened to the valuation? The valuation is anyway, on O star, the valuation is 0. On pi to the z, the valuation is exactly what you read in the exponent here. If the determinant of some element is pi to the r times invertible element in O star, then the valuation is exactly r. And the valuation, and the color is r modulo d. So you see from here that the image of G0 is exactly the subgroup of index D here, so we can conclude that G over G0 is exactly isomorphic to Z over dZ. It's a normal subgroup, and the image is exactly Z mod Z. You can see, you really can see exactly what happens here. You look at the determinant, and you look at the valuation of the determinant, and if it's 0, then you preserve. If it's not 0, you don't preserve. If it's not 0, it gets values between 0 to d minus 1, and it's kind of, it works like a cyclic group. So what I want, maybe I didn't write it in the most precise way, but I want to say that the element G, and that's important to remember, it pushes the colors in a cyclic way. You know, it always, G, if the valuation of the determinant of G is 3, then the action on the colors is always by pushing them by 3. You take a vertex of color I to a vertex of color I plus 3. It's not just, it's not acting as an arbitrary permutation on the colors. It's exactly pushing them in a cyclic order. Taking I to I plus a constant depending on G. And G0 is exactly those which preserve. So the action is simply done by a cyclic permutation of order D. Okay, these are little points that we will need at some point. Last point before we move. Let's see if this is last point here. Okay, yeah. What I want to say that why this last remark gives us a very important corollary, and this corollary is that why GLD does not preserve the coloring of the vertex, it preserves the coloring of oriented edges. So let me make this statement precise.
I showed this last time, so.
What?
I proved
Are you showing it? Okay, so I'll just say it now quickly. Given E equal L1, L2, an oriented edge, I mean in this direction, so going from L1 to L2, usually we don't orient edges, but I want to say, then the color tau of this E, we take it by definition to be the tau of L2 minus tau of L1 as an element of the group G mod DZ. And then the claim is, and that follows immediately, that GLDF preserve, or PGLDF preserves, that's really what acting, preserve the coloring of oriented edges. This is simply because they add a constant number. So if I add the same constant number to L1 and to L2, when I take the color of L1 minus the color of L2, then this is okay. Let me now talk about the link of the building links. Now this is something which we didn't have a chance to talk about, but something very important for general simplicial complex. So let's first define it for a general simplicial complex. If X is a simplicial complex and tau in X is some cell, some I cell. Can define it in general. We usually will be interested in links of vertices, but sometimes also links of other cells. So let's define it in general. The link of tau, or sometimes it's called the link of X at tau, is formally is the set sets of all subsets in order to define a simplicial complex, I'm going to define a new simplicial complex. I have a simplicial complex of X, and I'm going to define a new simplicial complex, which will be the link at tau, as all subset of the form sigma minus tau, where tau is a subset of sigma, and sigma is a cell of X. This looks a bit strange at the moment, but you'll see that it's something very natural and very intuitive. I'm taking all the subsets. What is a simplicial complex for us? We are taking a very formal definition. It's a collection of subsets of some set of vertices. So this is just a collection of some sets. I'm looking only on those subsets of X inside X which contains tau. I don't care about all the others. And now if they contain tau, I delete tau from them. Okay, so I'm getting some collection of sets. Now, this collection, in order to justify the name of simplicial complex, that this is a simplicial complex, what we have to check? We have to check that if something is in this collection, then every subset of it is in the collection, right? Okay, assume that you have a subset like in the collection which is of the form sigma minus tau, and you have a subset of it. Then a subset of it can be thought of some sigma 1 minus tau, where sigma 1 is inside sigma. And because of the fact that X is a simplicial complex, then sigma 1 is also in X, because a simplicial complex should be closed under inclusion. So sigma 1 is in the simplicial complex, and sigma 1 minus tau is in the link. Okay? So this is a simplicial complex. Now, what this really means, here is the simplest example. I have some kind of a simplicial complex. This is a simplicial complex. What you see, it's what you have. Like you have the triangles here, you have the edges, and you have the vertices that you see. And you ask, okay? And you ask yourself, what is the link, say, of this vertex? So, I'm looking at all the simplicial complexes containing that vertex, and I delete the vertex. So I have to take this edge, but then I delete this vertex, which means that I'm taking only that vertex. I'm taking the triangle here, but I have to delete this vertex. So now I have only the edge. The same way I have this edge. So the link of this vertex is simply it's simply this thing. These two lines and three vertices. Okay. Think of it in the formal way, because for me a triangle is not the inside of the triangle. I mean, I was just kind of I was writing it because to make it visualize. A triangle is a set of 3 points. I out of the 3, I deleted the original one and I stayed with 2. Okay, let's take this vertex now, and let's see what is the link of this vertex, of the middle one. So all the vertices, the original vertices, are connected to it by an edge, but I have to delete it. So I have to take all the vertices. And now, so every edge becomes a vertex, and every triangle, all the triangles containing it, but I have to delete it, so I have to take only the edges outside. So so the green simplicial complex is the link of the middle point. Okay? Now, here is a little exercise. The dimension of the link of tau, well, let's assume in general, let's assume, you have to be a bit careful if it's not pure. Assume X is pure, namely that all the maximal all the maximal faces are of the same dimension. That's what we are always interested in this course. Then the dimension of the link is equal to the dimension of x minus the dimension of tau minus 1, I believe. Why? Okay, well, here is the proof if you want. Of course, how do we get we have to really check what are the maximal cells. What are the maximal cells of the link? The maximal cells of the link are obtained by taking the maximal cells of X containing tau and then deleting out tau, right? So here is a proof. A maximal cell in L tau is obtained by taking a maximal cell M, say, of X containing tau. Now M, the size of M is equal to the dimension of X plus 1. And then we, a maximal cell, I don't know, we'll call it maybe M0. And M0 is equal to M minus tau, right? So the size of M0 is the size of M minus the size of tau. The size of M is a dimension of X plus 1 minus the size of tau is the dimension of tau plus 1, right? Because the size of tau is always the dimension plus 1. So the size of M0 is the dimension of M of X minus the dimension of tau. But this is the size of a maximal simplex, which implies that the dimension of M0 is the size of M0 minus 1, and that's exactly what we need, what we claim. That is the trivial exercise. But I know that I was confused about it, so I wanted to do it. In particular, and that's the case we will usually work with, if tau is a vertex V, then the dimension of a link at a point V is the dimension of X minus 1. Because the dimension of a vertex is 0, so dimension of X minus dimension of tau, this is 0, minus 1 is dimension of X minus 1. And now we are coming to the main point. I'll say it now, and next time I will start with it, a little bit elaborate on this, but that's kind of an important thing to see, and that will make the connection between the last 2 weeks and the previous few weeks. Claim if B is the building that what we defined today, B D of F, or last time and today, and V is any vertex in B0, then I claim that the link LV, the link at V The link at the vertex link is exactly what we call the spherical building DFQ, which is, if you remember, this is the flag complex of FQ to the D, of the finite FQ to the D. So it's a finite complex. You see, the building is an infinite complex. The link here is a finite complex. It's exactly that finite complex that we discussed in some details a few weeks ago. First of all, note that regarding dimension, it works okay. The dimension of B is D minus 1, and if you remember, the dimension of S DFQ was D minus 2. So that's okay with what we said. It's not difficult to see. I will come back to that. My time is over. I just say now, for the proof, note that as P, G, L, D, F acts transitively on the vertices, the structure of LV is independent of V. You see, in the example I showed you before, in this example, the link of this vertex was this segment of two edges and three vertices. This was the link of this one. The link of this one was this pentagon. So you see that the links can be very different depending on the vertices in a general simplicial complex. But in our complex, it's extremely symmetric, and all the vertices look the same because they're in action which takes one to another. You can forget about the coloring, but as a simplicial complex, what you see from one vertex is exactly what you see from other vertices. So we know in advance, we could know that all the links looks exactly the same. Okay? This is clear, right? That if you have transdirection. And the claim is this. Now, how to prove it? Then the way to prove it is look at L0. And just think, what are the neighbors of L0? And then you'll see that the neighbors of L0 are exactly the lattices between L0 and pi L0. You have to be a bit careful here. You have to convince yourself that, you know, I may have some neighbors of it which contain it, etc. So we'll discuss it a little bit. Next time I'll show you a more precise proof for that. But that's what we're doing next time, and then we'll continue with these things. So, okay, I prefer to do it a little bit slowly because I know it takes time to digest. The building is a little bit kind of an abstract notion.